Hey everyone, welcome to our think tank for the month of February here at the NfoLD webinar series on the topic of Mars sample return. I wanted to thank our two speakers, Roger Wiens and Maria-Paz, for joining us today. They're going to be talking about data sets that are being collected by the Perseverance rover supporting Mars sample return efforts. We're going to learn about the kind of spectroscopy that's possible with SuperCam, as well as the MEDA instrument, which I have to admit was new to me, which is telling us all about the environment on Mars. I also want to thank our steering committee members, Libby, Roland, and Claire, for all their hard work putting this together, and remind everyone that this will be our theme for the webinars for the next few months, really digging into Mars sample return, what it means for life detection. I know we don't often think of those samples as being possible for us to use in life detection studies, but really that's a great opportunity for us to test some techniques and hypotheses. It's a way to mature some of the technologies that are floating around in our group, and also explore the idea of life on Mars. We have a bunch of topics that we're going to be looking at over the next few months. Look forward to thinking about sample preservation and curation, as well as caching technologies, which I think is what's up next. I wanted to remind everyone that our format is to really discuss these topics at length. So after the public presentations, if you are online on Zoom as a steering committee member, please do stick around for enlightening discussion with our speakers and the assembled steering committee members. We'll try to think about how we might use these data sets in research that's relevant to topics within our group. And for now, I'll hand it over to Libby so that you can introduce the speakers if you would like.
Great, thank you, Heather. It is my pleasure to to introduce our two speakers today. So first we have Dr. Roger Wiens, who is a professor at Purdue University and a senior fellow at Los Alamos National Lab. He received his bachelor's from Wheaton College and his PhD from the University of Minnesota, and did a postdoc at Scripps Institute of Oceanography at UCSD. He was then staff scientist at Caltech and scientist at Los Alamos National Lab, and is now at Purdue. He's the PI of SuperCam and was the PI of ChemCam and member of Sherlock and Genesis missions. And so with that, I will hand it over to Dr. Wiens for his description of really exciting SuperCam results.
Great, thanks so much, both Libby and Heather. And I might say that you've really put together a great webinar series. I've looked at the last several, and it's really painting a really coherent story on what we are doing today with the Perseverance rover, as well as, of course, with other things for life detection and just for understanding the habitable environments. So I'm going to go ahead and first of all, I want to thank our team. And this is a team picture from last summer at the Sorbonne. We really couldn't have done this instrument without having, obviously a lot of people involved. But the other thing is that this is on the heels of the ChemCam instrument. And the backstory is that with ChemCam, we were operating and doing chemistry, but the science definition team for the Perseverance rover said that the remote sensing instrument had to do mineralogy. And maybe we thought we were sunk, but we put our heads together and we took the same architecture and we added several techniques, as you'll see, to do mineralogy two different ways. And we thought we were way out on a limb doing too much, but NASA liked that. And when they announced it, they said that we were doing a Swiss Army knife of instruments. So I'll introduce the instrument a little bit and then give some of the data that we have for Jezero Crater as this talk. And if I go too much over time, I think I do have too many slides. Just tap me on somehow and poke me, and I'll try to finish up faster. So I'm going to introduce SuperCam with these 5 techniques with a short video, and so let's see if it works on the webinar here. So SuperCam consists of 2 different major parts. So this is the mast unit. It has the laser and the telescope. It sits up on the top of the rover. And in the body of the rover, we have this body unit that has 3 more spectrometers, optical spectrometers. And then we have this calibration target that's at the back of the rover. And so this represents France, the US, and Spain in these three different areas. But together they do three different spectroscopic techniques. So the first one to be introduced here is laser-induced breakdown spectroscopy, which uses a focused laser beam to impart a lot of energy into one spot and create an atomic emission spectrum that gives us the chemistry. And then we use a green laser. The YAG is doubled frequency, and with that, we can get a remote Raman spectroscopy. It's unique to this particular instrument to do it remotely. And then finally, we use sunlight to get infrared reflectance spectroscopy for other mineral compositions. And then with that, we also have the imager, and the remote micro imager is actually the highest resolution camera, remote camera on the rover. So if we want to look at anything remotely, this has the highest resolution. It wasn't supposed to be that way. Mastcam Z was supposed to, but lo and behold, this thing really outperformed due to some small miracle shortly before the launch that I could tell you later. And then the microphone that is just being introduced there. And that microphone has told us a lot about the turbulence of the wind and other details of Mars' atmosphere. So that is the whole package, and we're really excited to have all of that together in one package. It really works well together, as you'll see. So this is just a little montage showing a few different details of that. If you can see my mouse, it is highlighting the upper left, where just the artist illustration that was on the proposal cover, showing these two different laser beams, sort of trying to show them at once, shooting at something that's completely inaccessible to the arm of the rover, which is one of our advantages. We can use these techniques with the laser out to about 12 meters, and typically we do it at shorter distance, but we can do LIBS and Raman spectroscopy ostensibly out to that. And then the LIBS is shown at the lower part, where we get this optically bright plasma, and it's because it's quite bright, we can just see it very easily with these spectrometers. The Raman's signal, on the other hand, is very dim. We, of course, use this green laser, and if I toggle this back and forth, you can see this brilliant green flash that we get from the laser. But the signal we get back in terms of the Raman, which is the shifted wavelengths that show us the mineral structure, are very weak. We're basically atom counting. So this is what we see with our spectrometer. This is laboratory results before we launched, but just showing different mineral structures here by the shift of these weak peaks that are off from the 0 point of the actual laser wavelength. And so we can see especially carbonates, sulfates, things like apatite, and then a few of the primary minerals like quartz and diopside, and then a few things like talc and so on. But we typically get fairly weak signals, and it turns out on Mars so far, the best signals we get are on the abrasion patches. We don't get, most of the time, we don't get very strong signals from the natural surfaces. And we've done some experiments, and certain Raman signals seem to actually wash out with UV irradiation. And of course, the natural surface on Mars is awash in UV radiation. So now, one of the key things for this instrument is the fact that we blow the dust off of any nearby samples before we do the other techniques. We do that naturally with the LIBS. And so this is actually an image from ChemCam. For those of you that love manganese and surface coatings, this is the target Stefan, or Stefan. But you can see that the dust was really removed from an area all around where we do our analyses. And you can see these pockmarks, those are the LIBS pits, but the dust gets removed from an area around that. And you can see it piling up and clumping at the edges of this. This rock is really only about the size of a US dollar coin. So it's not very big, but it certainly removes the dust from the area where we're analyzing. And if we do have different fields of view with our different techniques. So the infrared field of view is quite a lot larger than those LIBS pits, and so is the Raman. But the dust does get removed for all of these, and that's really key, like I said. So they work together very well. And then with the imager, this is showing the Kodiak delta remnant that was imaged right from the landing site basically on day 26 of the mission, as we were still unpacking the science payload, we took and started using SuperCam's RMI on long distance objects. And lo and behold, it was just really showed us some amazing detail that we much better than we expected. And so, for example, this showed the Gilbert type deltas that this is displaying with this delta remnant, and then also the delta front, showing how this goes down into the lake bottom, basically on these four sets. So really showing that very clearly that this was a delta formation. And then in the near distance, we can use SuperCam's RMI to really point out some amazing things. And we use SuperCam just about every day. And so it's used a lot more than the rover's arm. And so we have a lot of these images that really show a lot of the texture and morphology of these rocks close up. This is from the Seta formation. This is in false color. It really should be an olivine color here because these are olivine crystals on a fresh rock surface. But the inside, the inset on the lower right part of the image shows the NavCam image, and you can see this is a ways away, several meters away, and yet we can see all these millimeter-sized mineral grains. And so this RMI is just a really amazing tool to use for these morphologies. Okay, I'll take you now to Jezero Crater, and we'll talk about where we've been and a little bit of what we've done with this data set. So we've explored well, first of all, we explored the floor of the crater in these regions of Seta, which is an olivine cumulate, and then Maz, which is a volcanic or igneous unit as well, covering a lot of the crater floor. But then from there, after the first year, we went over to the delta front, and we spent nearly a year there as well. And then just over a year ago, we went up onto the delta top, and you can see where we are as of just 2 days. In fact, we're basically still there now. We're just a few 20 meters away from when this picture was snapped. And so we're on the edge of the marginal unit, and we'll be heading into God willing, Nerette Vivalis, and then up onto the crater rim. So what have we seen in these areas? Well, I'm going to focus, since some of the earlier webinars were on the crater floor and the delta front, I'll talk a little bit more about the delta campaign itself. And so we were looking for the paleo environments, regional and global climate, some of the durations, how long was this delta in the process of being built, how long was the lake, what was the composition of the source rocks, and then what's the provenance of the delta sediments, what is upstream, and looking for physical modification, the burial processes, erosion, exhumation, and then what does that do for potential organics and biosignatures? Is it preserving them, and where would it be preserving them best? So these are all some of the major goals. And just looking quickly at a stratigraphic column of the delta front, this is what it looks like, at least in one of the three sort of areas that we investigated. And so we might have thought that we would see a lot of fine-grained material, but we've actually seen more coarse or medium-sized grains than we expected, and not as much fine-grained material. We did find one area, as the arrow shows here, in the Hogwallow Flats area that we really got down to light tone siltstones, and they contain sulfates, likely from a period of intense evaporation, but also look down at Devil's Tanyard, which is just a little bit lower. The regions in between were either there's an igneous or potential igneous unit, and then one area that was covered by sand that we didn't really get much of a view of. So Devil's Tanyard is exciting and interesting, and then Hogwallow Flats. Those are the ones that we were kind of focusing in on. So let's take a look at some of the mineralogy as we see from the infrared spectrometer. And by the way, this helps us to calibrate other infrared spectra from all around Mars. And so you'll see CRISM spectra, that's the orbital spectrometer that's over on the right side of this and the next slide as well, or actually just this slide. But what we see in these spectra on the left, let me just interpret this for you. We have, first of all, on the left-hand side, we've got a big dip at 1.4 microns. That is a that is a phyllosilicate band. And so we're seeing that in spades here. Then in the 1.9 micron region, we have a big dip. This is a water absorption band. And so this is very deep. And so we have a lot of water absorbed onto these minerals as well. And then going to the right at 0.3 microns and 2.4 microns, those as well are magnesium and iron absorptions for like smectides and so on. But we think overall, this overall signature is basically a vermiculite signature. These are hydrated iron magnesium phyllosilicates. So pretty exciting to see this here. It's really what we wanted to see at the delta front, and SuperCam really delivered the signal. That's at Devil's Tanyard, so it's again, it's sort of a sandstone size grains, medium sand, you could say. But at the Hogwallow Flats member, which is just a little bit farther up, it's what we see as a bacon strip, this light and dark toned alternating material just below the cliffs. And here we see some other features. We still see that strong water absorption feature at 1.9 microns, not as much 1.4 on the left, but over on the right, we have a sort of a big drop at 2.38 microns, and that is indicative of sulfate. But we still see some things at 2.3 microns that there's still phyllosilicates here. And again, so pretty exciting. And as you know, for life detection and that taphonomy is best, or that is preservation of organics is best in fine-grained materials and of course with phyllosilicates. So this is where we collected several samples, and that's exciting. I'll take you now to some diagenetic features that we saw right in this same area. So there's some nodules or concretions, and Himani Kalucha is finishing revisions on a paper on that. We have veins, especially anhydrite, but we also saw some carbonates. And Marion Nachon is working on a paper on that. And then we have manganese coatings. And this was really exciting, especially for people interested in life detection. Now, these coatings are very thin, and so the spectra, with these peaks that you're seeing in the top of that slide, are showing successive laser shots into the same spot or spots on this coating, and showing that we're actually profiling right through them with a few laser shots, showing that they're only about 30 microns thick. That's suggestive that they're pretty recent in time, very intriguing. We thought about getting a sample core right onto this, but because these things are only 30 microns thick, it's like, well, would we get it? Would we not? And we think that we probably had almost as much likelihood of getting it with bear wallow, which is just less than a meter away, probably picking up some grains from this. So that is of interest if you are very interested in manganese coatings. So keep that in mind. Now, moving on, we then moved the rover in this last year through the curvilinear unit. It was dominated by apparent point bar features, coarse sandstones, and it is olivine rich. And then we got into the lobe unit, the delta lobes. And so these are, again, coarse grained sandstones, olivine rich, but also now have some plagioclase, some silica enrichment, some sulfates and carbonates. And we had lots of boulders. So now I'm going to show you just a little bit of the chemistry of this. First of all, this is Zeta, and I'll orient you to this plot just a little bit. So on the left is, lower left is silica. On the lower right is all of your mafic materials, your iron and magnesium. And on the upper part would be your felsic materials. And if I show you the mineral compositions, they lie just like this. So olivine sort of down and a little bit to the right, orthopyroxene more to the middle at the bottom. Clinopyroxene with its calcium is up here, and feldspar is to the left. And then if you have anything that's high in silica, it would be over towards the lower left. And then something that is lacking in silica, which would be carbonates and sulfates, are kind of antipolar to that over here. So now let's look. So the Zeta is this olivine cumulate, and so you see a lot of the olivines there, but of some orthopyroxene, a bunch of clinopyroxene. One other thing that we see.
Inside the warehouse is a factory run by Ukrainian Armor, one of the country's biggest weapons companies. Bogdan supervises mortar production here. He declines to give his last.
Sorry, something turned on here. Let me go back and get you back on this. So hang on here. I hope you didn't hear that interference like I did. Okay,
I was trying to figure out if that was me.
yeah, I wasn't sure who it was either, but I figured it out. Sorry. Yes, where we were is that we have a bunch of dust crusts, and these are coating the rocks, and so they're sitting in the middle of this, and so just be aware of that. They're almost identical to the dust composition. So they're a bit of a contaminant, you could say. So now when we go to the curvilinear unit in purple, you start to see a little bit of some differences. We're not seeing the feldspars here. We're not seeing clinopyroxene, but we are seeing a little bit more high silica and then a bunch more sulfate and carbonate over here. So that's what's now characterizing some of that delta top region. And then looking, and here's my points that I was just saying, and then looking at the bedrock of the lobe region, we have much the same, but actually even more of the high silica. So that's pretty interesting. And more of the carbonates as well. So getting towards this marginal unit. So now just a quick peek at some of the infrared spectra that we're getting from some of this area as well. And you can see that there are still thylosilicates with all of these little wavy bumps in here and this water signature here. And so but it's got the signature also of some magnesium iron carbonates as well. So that's pretty exciting. All right, this is the overhead view of when we went through the delta lobes. And one of the things that characterizes this is a huge number of boulders. I don't know if you can see it on your screen, but there's just a lot of sort of little grisly sort of features to this image. You don't see it in a place like Parika Lake. For some reason, that was amazingly absent of boulders. But most of this had a lot of boulders. And so we also went to characterizing the boulders. So I'll point you to Mount Meeker, which is an interesting boulder that we're going to see here. But first of all, just pointing out that from the landing site, we saw these boulders embedded in the delta front part way up, but we also saw them at the very top. And so that's what we're looking at now, is all the boulders that are on the delta top in the lobe unit now. And so this is what it looked like. And in fact, putting in a Mastcam Z 110 millimeter of Mount Meeker, it looks like this. And so Mount Meeker was this really gnarly looking boulder, and we could start to see two populations of boulders. And compositionally, they really stood out to us. In some of the lobes, we have 75% of the boulders that are just olivine, a lot of olivine. But then in 1/4 of the boulders we have low calcium pyroxene and plagioclase rich. And that is Mount Meeker. Mount Meeker is one of these. And so we drove over to Mount Meeker to try to sample it. We broke the bit, and we have more than one bit, so that's fortunate. But this is a really hard rock, and we have used those bits on basalts terrestrially in the lab. So this is like harder than terrestrial basalt, and we're really puzzled about that. But in other lobes, we just saw 100% olivine rich, similar to the Seta cumulates, effectively. And there's some weathering differences on these as well due to their hardness and so on. So you can see our infrared spectra are extremely different between the olivine and the pyroxene. So it's just real easy to pick them out. And then compositionally with the elemental compositions, that was easy as well. And so the orange is olivine and low calcium pyroxene, whereas the blue is the pyroxene plus plagioclase. And so we have this two very different populations coming from upstream. Okay, so now we're going to talk about the marginal unit very briefly, and I'll try to finish up. So we've spent the last 4 or 5 months in the marginal unit, so we started to see that one of the things that we think that the orbital signal that is giving us a lot of carbonate in this region is from the soil. And so this is what the soil looks like. The soil there was just pockmarked full of these tiny little pebbles. They were about 1 millimeter to 2 millimeters. And it turns out that they're carbonate rich. And so that's pretty cool. So I'm showing carbonate signatures over here on the right. I won't talk more about that, but look at the rocks. Some of these rocks are really rough. And this rough texture looks, if we look at it real closely with the RMI, we can start to see these rounded things just weathering out. And those things are the same size as the pebbles that we're seeing on the ground in the soil. So it looks as if the carbonates are rounded and they're weathering out of there, suggesting that carbonates, at least some of them, are detrital here. So let's keep that in mind. Another thing that we've seen in this area is a lot more silica, and so it seems to be different places. That would suggest authigenic formation of carbonates because a byproduct of that is silica. So maybe we have both authigenic and detrital carbonates coming in the margin unit. But here we have a very interesting rock because this rock is entirely silica. And so the signature on the right is hydrated silica, like opaline silica, and both our infrared and our libs just showed this rock to be very high silica. And you're going to hear more about it if you go to Lunar and Planetary Science Conference from Pierre Beck. Just remember that silica is of strong interest for astrobiology because it's an excellent preserver of ancient organics on Earth. Okay, one other thing that we saw along the way, and we've seen this all along the way, is float rocks that are aluminum rich, and these things stick out like a lighthouse because they're so light toned. This one here looked like a dinosaur's tooth. But they consist of high aluminum. They're like 35% aluminum, and the rest is silicon. And so these are the products, apparently, of very strong aqueous alteration, and potentially followed by some metamorphism that would then solidify these pedogenic materials into a solid rock. And so we've got a paper on that and it working its way through as well, and you'll hear more at conferences about that as well. So again, some very tantalizing stuff, only in the form of float rocks so far. So let's see what we find sort of up the trail. I'll just finish with a summary saying, first of all, SuperCam is a comprehensive instrument. It really provides a lot of different things, both mineralogy and chemistry, which work so well together along with this imaging. So what we've seen is that Jezero Crater had a complex history. Just looking at little snippets of it, this igneous bedrock in the crater floor, boulders in the delta indicating periodic catastrophic flooding. But then, the lake was many tens of meters deep at times, but the main fine-grained deposits that we saw are in a narrow area. And this Hogwallow Flats suggests extensive evaporation, but also lots of phyllosilicate, so very good for collection of samples. And then the carbonate and silica, they're increasing towards the marginal unit. It's still dominated by olivine. And we talked about both authigenic and detrital potentially. So one question is, what are we going to find in the regions up ahead? And I think we have some hints. We may find some more opaline silica bedrock. We could find heavily altered or metamorphosed deposits related to impact perhaps, but very aqueously altered. And we may have some impact breccias as well, shatter cones and glass. I just saw an image that's very suggestive of glass that I'll show at the Lunar and Planetary Science Conference as well. So, lots of things to look forward to. And this mission is now almost exactly 3 years old, almost to the day, and we're looking forward to a lot more ahead. So thanks a lot for the opportunity to give this talk.
Great. Thank you very much, Roger. So now the format is Maria-Paz will talk, and then we'll have questions from everybody and then the discussion. So it is, thank you very much for that really, really interesting and great talk. That was really fun. So now it is my pleasure to introduce Dr. Maria-Paz Zorzano. She is a senior research scientist at the Center for Astrobiology. She received her PhD from the University of Madrid and did her postdoc at CERN in Switzerland, and is a member of the science and operation teams of several Mars missions, including Curiosity, ExoMars, Rover and Trace Gas Orbiter, and Perseverance. And she will be showing us some very exciting results from MEDA. And I will turn it over to you.
Thank you. Thank you so much. Sorry, I stopped sharing the screen, but there I go back. So thank you for inviting me here today. I'm going to focus mostly on how the present day environmental measurements provided by an instrument called MEDA can be used to infer something about life. And as we're in this forum, how to detect life. I'm going to focus more on present day life or life that was there sometime near in the recent time, because the environmental measurements obviously are only telling us something about the temperatures and the water cycle nowadays. First of all, so why do we care about the environment at all when we define conditions for life, or when we talk about habitability on Mars or anywhere in the universe, in an exoplanet? When we talk about habitability, we're talking about water availability and temperature at large scales. So one way of investigating this, and it was my original approach, is talking about planetary protection. So at least we know how life is on Earth, and we're bringing all this spacecraft to Mars, and we want to make sure we don't bring contaminants that can reproduce on Mars. And generally, we say Mars is too cold and too dry, so life as we know cannot reproduce. And that is roughly correct. But that has to be demonstrated with measurements, right? So for planetary protection, or just for life itself, we know water is a requirement. And then from measurements on Earth, we have a parameter that is called water activity, that basically tells you how much water is available for metabolic or reproduction activities in cells. Now, sorry, this water activity has been investigated under controlled conditions in the lab. And then there are limits for the amount of water that can be tolerated, or the lack of water that can be tolerated. And we have a record with this halophilic fungus that can tolerate this low amount of water activity. Just that you know, under certain conditions of equilibrium, this value ranges between 0 and 1. 1 is the maximum. You have full liquid water availability, pure water. And you can obtain it by knowing the relative humidity in the atmosphere above and dividing it by 100. So this is kind of in the middle of the range, and it tells you that there are extremophiles on Earth that can tolerate the absence of water. But then the other parameter is temperature. And we also go to extremophiles, and we look for these guys that can reproduce at very low temperatures. And then you have a pink yeast called Rhodoptera glutenis that can actually reproduce at minus 18 degrees. And it's important that we take these two parameters as the limiting environmental conditions required for life as we know. So when the panel that is defining the planetary protection procedures, the protocols, the measurements, they look at the literature and they find these record extremophiles, then they say, okay, we define habitability conditions at large scales as those that meet simultaneously water activity above 0.5. So they have added some margin in case there is a new discovery in the years to come, and temperatures above 245 Kelvin, which is it has a margin of 10 degrees. So this is life as we know. But of course, 10 years from now, we will know about other extremophiles, and that's why we have to document what is the actual water activity and temperature on Mars. And anyway, if these are the conditions on Earth, it's understandable that the organisms that we know are adapted to a very humid and warm life. But if it ever existed on Mars, it presumably should have adapted to an environment that was colder and drier over the years. So with this view in mind, we have the landscape on Earth of a very dry region. This is the Atacama region, where we know there is life underneath the surface in very dry conditions. And we have the landscape here. This is an example from a Gale crater, but it would be equivalent in Jezero crater. And this is the scale of water activity that I was telling you about. It goes from 0 to 1. And if you're above this limit, then maybe you have cell reproduction. But if you're below, you only have cell growth. And that means that eventually you may have metabolism, you may have survival, but eventually this cell will die. So that's why we're going to pay attention to the relative humidity and the temperature. Now, at larger scale on Mars, we have been measuring the water cycle from the surface and from orbiters at different regions of the planet. And we have measurements, similar measurements to the ones provided by MEDA at Jezero crater. We have them from REMS measurements at Gale crater. I'm going to show a couple of examples. But the idea is that what we observe is that during the night, when the temperatures of the surfaces drop, there is an absorption phenomena of water moisture of the atmosphere into the rock, the regolith, and the salts that are within the top centimeters. And then during the day, this water is released back to the atmosphere. And eventually, if you look up in the sky, you have cloud nucleation, so you have small crystals that are formed. And if you go to the polar regions, then maybe you have permafrost or frozen water. Now, because we're looking in latitudes that are near the equator, the water cycle is going to look like this, and this is what we are monitoring with the instruments on board platforms like Curiosity and Perseverance. The data are always provided with a timestamp because we are measuring every day at different hours over the day. This is an example of the volume mixing ratio, the amount of water that it's in the air at Gale crater during different sols, different days of the emission at different hours of the day. And generally you see how you start having at 21 hours in the evening, a high value, and then this is decreasing as the water is being presumably absorbed by the regolith. Now, these measurements were taken at Gale crater, but we have something similar with this decrement over the hours over the night provided by MEDA measurements at Jezero crater. And what I want you to look at is this amount of water in every volume of gas, of CO2 gas. We have tiny amounts of water, but because the temperatures are so low, the relative humidity is very high. This means that during the last hours of the night, the conditions on the surface are such that sometimes saturation is reached. And this is important because at the end, what we want to do is to calculate the water activity. And remember that the water activity depends on the relative humidity. Now, if you are interested in having access to the data provided by MEDA, I encourage you to go to the planetary data system. All the data are archived there. They're explained with all the labels. And you're going to get information not only from relative humidity and ground temperature, which is the information that I'm interested on, but you also have access to the pressure, which is another important parameter for the samples, and I will explain to you why. And also we're monitoring the sky with a camera. You have wind sensors, and you can also have a sense for the amount of dust that it's in the atmosphere and it's circulating over the region. This graph here is an example of the accumulated information that we can obtain with MEDA. We are measuring over consecutive sols, and here is a graph that is produced for every sample. When we are sampling and sealing the samples, we want to know what was the temperature and the pressure in the region where we were sealing so that we can calculate how much gas is within the sealed sample. So for every sample, we are collecting here, let's say this is the name of the sample. We know on what day it was drilled and sealed, at what time, so we can know what is the solar longitude, at what moment with respect to the orbital evolution around the sun it was, so it could be spring or winter. We know the air temperature, the pressure. These are measurements provided by MEDA. And then we know, we take a measurement of the length of the rock that was sealed with a probe, an external probe. This is only an approximate measurement, so there is a lot of error here. And from that, you can calculate how much, what is the volume of the rock that you think you have, what is the mass, if you make a guess for the density, so this is already making a big guess, and what is the volume of the gas that you have encapsulated within that tube. So that's important because actually the Mars sample return mission not only has a requirement to bring an amount of rocks, and here so far we estimate we have more than 350 grams of rocks sealed. This was a collection that was prepared just before making the depot at Three Forks. But we also have some moles of gas, and that is very important because actually this will be the first sample collection that includes an atmospheric sample from another planet, right? So we have meteorites from Mars. Obviously, they have been very altered, so they are not pristine. But there's no way that we have some gas from a pristine gas from the atmosphere brought with a meteorite nowadays. So as I said, for every sample that we are sealing, We're documenting all the information provided by the instruments, and you can have access to these initial reports, we call them, at the PDS node. So for everyone, you have like the field campaign notes, what we know at that moment, how it looked, the rock, how it looked before we approach it, how we interpret the abraded patch information, and also what is the amount of gas that we estimate that has been sealed within the sample. And as I said, this is going to be amazing because with all these molecules that are in the gas, there are all the scientists in the future that may want to look at the isotopes of some of these elements, obviously to look for maybe methane. That would be, I'm afraid, very hard because the amount that we expect to have is really ridiculous for the sensitivity of the instruments that we have nowadays, but maybe not in the future. And as a conclusion from these environmental measurements, we can already estimate that we have fulfilled one of the requirements of sealing Martian atmospheres in the samples and making them available so that they are brought to Earth in the future. Now, regarding the rock samples, we know also from the abrasion of the rocks, for every sample that we take, before we take that sample, we abrade nearby, and we do in situ analysis with other instruments to understand what is the rock, what is it composed of. And for some of these rocks, I'm giving here an example of one of the articles provided by one of the team members. We have found so many salts. We have found up to 82% of sulfates and up to 64% of perchlorate, just to give a few examples of salts. So why is it this is important? Because we were saying before that we think that the water that is contained in the atmosphere is being trapped by the soil, by the regolith, by the rocks. It's acting like a cold trap. But if you have in this bedrock or in the regolith, if you have a small amount of salts, some of these salts, when they're in contact with water vapor, they're going to hydrate. So the question is, may these salts have captured some of the water? And why is this important? Because it happens we know from Earth that there are microorganisms that can survive using water that has been absorbed by these salts. I'm giving here an example of a graph that is included in the paper by Libby Hausrath and colleagues. And this is an example of in situ examinations in general of the soil at Jezero crater. But I'm showing this example because it includes how we can use the MEDA measurements, the relative humidity and the ground temperature. They are taken simultaneously over different days, and we can compare them with the phase diagrams of some of the salts that have been reported. And what this is telling you is that if we have sulfates, magnesium sulfates, or calcium sulfate in the rocks, when they are exposed to this diurnal cycle, they're going to absorb water if they are in contact with the air, and they're going to release it back to the atmosphere during the day. So we expect to have calcium sulfate with 2 molecules, or magnesium sulfates with 7 or 11, and so on and so forth. Obviously, this is what we expect to happen at the top of the surface, but as you go within the rocks, the temperature profile can change, and this interchange of water is not instantaneous. So you may retain in some regions water, whereas some other regions may release the water immediately. Regarding habitability, we can have this kind of graphs again. So now we're plotting water activity, so relative humidity divided by 1. I'm showing here by 100, showing here the measurements from REM's instrument at Gale crater, but the dynamics is similar. And you're comparing it with the measured ground temperatures. And now we're comparing it with the phase diagram of calcium perchlorate. And I'm doing this because this salt is the one that has the lowest eutectic temperature from the ones that we know that exist on Mars. If we ever have conditions that go above this region, then you're going to have a different phenomenon. Not if you go across this boundary, you have hydration, but when you go inside this region, you have deliquescence. That means that the salt can absorb so much water that it actually melts into a liquid brine. And these brines are not very nice to live in, at least for the known microorganisms on Earth. But you may imagine that if you have a mixture of salts that survive in liquid state at very low temperatures and very low water activities, and you were coming from a past time where the environmental conditions on Mars were over here, you can imagine that life should have adapted to evolve and survive under these conditions. Now, these are the conditions for life as we know on Earth. These are the conditions that we are experiencing on Mars nowadays, at Jezero crater and at Gale crater. And based on these measurements alone, using the parameters that we know from Earth and the observations from MEDA, we can say that we don't expect cell proliferation to exist nowadays on Mars. So there's no life as we know. You can take this model for other latitudes on Mars. Let's say this could be what we expect again at Jezero and Gale crater. We're going underneath the calcium perchlorate eutectic point, but you can compare it with other eutectic points. And if you go at polar regions, you would have this kind of behavior, because we have had measurements in situ also with environmental instruments with the Phoenix lander. And you can see that now we are above the eutectic points of some other sulfates. So you could have liquid brine formation in these regions. And if we manage to have more water available, eventually you would have these salts in a liquid brine state. So the way we can use this data in our labs nowadays to prepare for the mass sample return, at least this is what I propose, is to make simulations in environmental chambers of the materials that we have on Mars under the environmental conditions that we are measuring. And I'm showing here an example where we have investigated different salts that are on Mars, regolith mixed with 10% of the salts, and again, another set of experiments with salts under different conditions. And we put them inside what we call a Mars chamber, where you can inject water and you can control the temperature. And this is what we're doing here. Over time, we're injecting water and we have very low temperature. The temperature is increasing very slowly and the water activity or relative humidity, it's at 100%. So we have saturation. And this is our experiment. Here is our Mars in a bottle experiment. We have regolith with 10% of different salts. And what we observe is that this regolith can absorb as much as 50%, 18%, 36%, 30% of its weight in water. So if a microorganism could live upon this water, that would be fantastic, wouldn't it? Because then we would say that Mars is habitable nowadays. So we are doing experiments to help our experiment run in real time. We're running them at ambient temperatures, and that's cheating a lot. But we are running now experiments where we use some tiny amount of rock, like half a gram, and we put it in contact with water only through the atmosphere and let it absorb water. And then we extract the products that are inside the regolith. We try to extract DNA and analyze it with an instrument that is called MENA-ion. And it's super fun because actually we see that when you expose this regolith, which is from Earth, let me say, it's an analog of a Martian regolith analog, but it's obviously from Earth. We expose it to 80% relative humidity, which is about 8.8 water activity, and we incubate it over days. We can see that we go from having non-detectable DNA to having significant DNA. So the bugs that are there are happy with this water. That's enough for them to reproduce. And then we can sequence it, and it's still tiny. It's just picograms, but we find very interesting microorganisms that are absolutely fascinated by this environment. They love it. And maybe they could even be, they could survive on Mars because they are resistant to radiation like gamma and UV. But the most discouraging thing is that we had to work in an ultra clean room, and obviously everywhere, including in our products, there was human contamination. And this is important for the Mars sample return program, because if this was a Martian sample, we should make sure that we have no contamination of terrestrial microorganisms that have gone through the air or through the filters or through the products that we're using. And obviously, our manipulators, our human manipulators, are going to be contaminating everything also. So with that, I would like to summarize that the environmental conditions at Jezero crater are not adequate for the liquescence because we're going underneath the eutectic point of the last salt that we know can be in liquid state, but they allow for calcium and magnesium sulfates to hydrate. We know from Earth, from the Atacama Desert, that there are certain cyanobacterium that could extract water from this gypsum. So it has not been documented if these cells can reproduce. It has not been documented exactly what was the water activity, but this is the research line that I think we need to proceed on. So based on the state of the art, what we know now, the limits of life on Earth, we conclude that the environmental conditions of the samples and of the surface of Jezero crater are not compatible with our known cell replication requirements. But I would encourage everyone to investigate the extremes of life on Earth at lower temperature limits and lower water activity, and especially if there are any microorganisms that can extract water from salts or from the regolith when it has been absorbed. So that would be it, and I'm looking forward to hearing your questions.
Thanks so much, Maria. I was just commenting that my co-lead Alfonso, who's on a plane right now and couldn't join us, has done field work in that area, and I would have loved to hear his comments. Since it's just us, Sean, are we still on the YouTube Live, or have you stopped